So again, by definition, a graph is bipartite if it has a bipartition, and that's a way of splitting the vertices into a left set and a right set so that every edge has one end in the left and one end in the right. So that's our basic definition. Now what we're going to do is prove a very key theorem that gives an alternate characterization, actually two different alternate characterizations of what it means to be bipartite. So let's get rolling with that. So for every graph G, the following are equivalent. I'm just going to write this. The following are equivalent, TFAE. Actually, maybe I'll leave those dots out. For every graph G, the following are equivalent. So the three statements are: 1, G is bipartite. Statement 2, G has no cycle of odd length. And 3 is G has no closed walk of odd length. Now, so I want to prove that all three of these statements are equivalent. So again, a graph is bipartite by definition. If there's this bipartition, this split into a left and right, so that all edges go from left to right, we're going to prove that that's equivalent to the statement. So the graph being bipartite is equivalent to the statement that the graph has no odd cycle. And that's equivalent to the statement that it has no closed walk of odd length. So we just have three different equivalent ways of saying the same thing here. I'm not sure how much this proof I'm going to manage to write here. At least I'll do the first part. So in order to prove this, what we're going to do is we'll prove that condition 1 implies condition 2, condition 2 implies condition 3, and condition 3 implies condition 1. Right, so if we've done that, then we've established that all three of these statements are equivalent. If any one is true, then all three will be. Now 1 implies 2 is, this is fairly immediate. So if I give you a graph that is bipartite, that means I have this split of the vertices into a left set and a right set, and every edge has one end in the left and one end in the right. Now if you're going to make a cycle, you have to alternate, right? You have to take a vertex on the left, then a vertex on the right, then a vertex on the left, then a vertex on the right, and a vertex on the left, and then a vertex on the right. And if you come around and make a cycle like that, then every second vertex will be on the left, every second vertex will be on the right, because that's what it has to be. That's the rule for every edge. Every edge goes from left to right. And in that case, you're going to have necessarily a cycle of even length, right? So what that means is if your graph is bipartite, then every cycle will have to have even length, or equivalently, there's no cycle of odd length. Okay, so condition 1 implies that condition 2 is true. If you have a bipartite graph, then it will not have a cycle of odd length. So I'm just going to write a little check mark here. So now let's show that 2 implies 3. So now I have a graph that has no cycle of odd length, and I want to prove that it has no closed walk of odd length. And now there's a good way to think about this and do this. In these graph theory settings, you always want to kind of turn things around and think about a proof by contradiction, or think about the contrapositive. I'll say you want to be a little bit facile at moving from one of these to another. I will say that usually it's a good idea to take advantage of something that allows you to kind of have a structural property of the graph. If you can say some property that tells you something nice about what your graph is, that your graph has a feature, that's very nice. You see what we're proving here? G has no cycle of odd length. That implies G has no closed walk of odd length. That's an annoying thing to work with, right? G doesn't have this thing. If you just say contrapositive here, or you say contradiction, suddenly you're in a much nicer setting. So again, just as written, 2 implies 3. That reads, G has no cycle of odd length implies G has no closed walk of odd length. If we take the contrapositive, right, so the contrapositive, if I have the expression A implies B, then the contrapositive is not B implies not A. And when I negate these, I suddenly have a structural property that I can take advantage of. There is something instead of there's not something. And that's really a thing you want to look to do when you're trying to think about problem solving and trying to think about understanding these things and writing down a proof. So let's say that what the contrapositive is in this case. The contrapositive is going to be, so our B expression here is G has no closed walk of odd length. Negating that means there exists a closed walk of odd length. That's much nicer, right? If I tell you a graph has a closed walk of odd length, that's a thing I can grab a hold of, right? Here it is. It's V0 V0, E1, V1, E2, so on, onto Vn, and V0 and Vn are the same, and it has odd length. That is a structure. Maybe it's not an exciting structure that tells you everything, but it's something you can instantiate and take advantage of, right? I'm telling you the graph has this, right? So the contrapositive here, let me just sort of say, so we're going to do the contrapositive, which is not 3 implies not 2. So we're proving, I'll just write it out in words, not 3 implies not 2. But again, this is so much nicer. So now what's not 3 means there exists a closed walk of odd length. Not 2 means there exists a cycle of odd length. So now we're trying to prove that if I give you a graph that has a closed walk of odd length, then it has a cycle of odd length, right? And you know what, so a closed walk, so somehow you're going around and coming back to where you started, and you took an odd number of steps, right? You traversed an odd number of edges. Now, if that closed walk that I gave you had no repeated vertices other than the first, which equals the last, then you've already got it. Then the vertices and edges forming that closed walk, that is going to give you an odd cycle, and then you're done. The only other thing that can happen is you sort of walk along and intersect yourself. Maybe you walk along the same vertices. You're allowed to walk along the same edges too, but you're going to walk along some vertices and edges and come back to where you started. But you step on the same vertex, or there's the same edge more than once. But that's a thing that we can ask for. So suppose I give you a walk that doesn't just start and end here, but has some other repeated vertex. What are you going to do? And now there's a thing that's pretty natural. So if you start here and go and say you repeat a vertex, say vertex Vi equals vertex Vj. Like, I don't know why I'm drawing a picture up there. I can draw it on the page. So here's maybe of a walk that starts here. Let's do the easiest case. There you are. So this might be vertex V0 equals Vn, and this might be vertex Vi equals Vj. So there we are. So I'm looking at a walk here. let me write it down. So let's say I'm going to choose a walk W, which is the walk V0, E1, V1 on up to E sub n, V sub n. So there's some walk. And it's closed walk, so V0 equals Vn. And now suppose that you saw a repeated vertex somewhere else. I tell you that Vi equals Vj. And I'm sort of drawing here on the page the very simplest thing that could happen. So you start at V0, walk along to Vi, you come back to that same vertex. So Vi is going to be Vj, and then you finish off. So here's a little figure 8. Now, if I take our assumption now, what's our assumption? Our assumption is that this closed walk is odd length, right? So now I have this closed walk that's odd length, but you see that the closed walk I can just break up into 2 closed walks. You can walk from V0 over to Vi, and then that vertex is also Vj, so you can just continue around from Vj back, and then you have another loop out here, right, from Vi back to Vj. So that allows me to take a closed walk with a repeated vertex and split it into 2. Well, if the first one was odd, the length of the first one is the sum of the length of the 2 pieces I've broken it up into. If the first one's odd, then one of those 2 pieces has to be odd. And I'm going to find a shorter closed walk, which is odd. So what I've done here is just sort of real-time talked my way through the solution to this, right? Again, we have the key ingredients here. We have jumped to the contrapositive, and I hope you realize here that looks good because the negations of these statements are giving us things that we can grab a hold of in our graph. That's always a thing we want to look for. We love statements that are there exists blah, there doesn't exist blah is a lot harder to operate with as an assumption. I mean, sometimes we need to, but it's a lot easier to grab a hold of something that gives us a graph structure. And so we are going to look to do that. So here we've taken advantage of this presence of the closed walk of odd length, and we're kind of just observing that, okay, if you give me a closed walk of odd length, if there were no repeated vertices other than the first equals last, then you've already got your odd cycle. If you have a repeat, then I can see what's happening. Okay, then either this part's odd or that part's odd, and you're going to get a smaller one. And that's right. You can absolutely express this argument in that manner. A somewhat cheaper way to do this is to kind of cut through it a little bit cleaner, is to just try to choose a shortest possible closed walk of odd length. So what I'm going to do to write the proof, and again, there's a little bit of a stylistic ingredient here. There are many ways of writing out a valid argument for this, but the one I'm giving you is quite clean and simple, and it doesn't have an algorithmic aspect in the sense that we're not going to have to iterate something. I'm just going to choose an optimal one, and we'll verify that that optimal one has the desired property. So what we're going to do is so now we'll choose a closed walk, choose an odd closed walk, there it is, of minimum length. Let me just write it all here. So I'm sorry, my writing isn't a little bit better, but so what I'm going to do is I'm just going to choose again, a closed walk of odd length that's as short as possible. And what I'm going to do now is I'm just going to claim that this actually doesn't have any repeated vertex. So the claim here is the only repeat is that V0 equals V sub n. And the proof of that claim, I'm just going to proof of that claim is what? Well, let's suppose otherwise. And again, supposing otherwise, we've got a thing that happens. Then Vi equals Vj, where I comma j, where I is less than j, and I comma j is not 0 and n. It's not the first and the last. Suppose I have vi equals vj, and now we're just going to do this argument. If vi equals v sub j, I can break the whole walk into two pieces. Now I can make a closed walk. I'm sorry, I'm just short of space here, but I can make a closed walk that starts at v0 and then e1 and then v1 and continues along to vi. Ordinarily, after the vertex vi, you'd continue with the edge ei plus 1, according to my indexing, but I know that vi is the same as the vertex v sub j, right? Vi is the same as v sub j, so I could take advantage of that to just continue along on edge e sub j plus 1. And continue along to vertex vn. That's a perfectly good closed walk. Again, this one's vn equals v0, so this goes from some vertex back to itself. I also have another closed walk that's sort of the inner piece here that starts off vi and then ei plus 1 on up to v sub j. Right, and all I'm drawing I'm just drawing what or writing out the the symbols that give me this picture. Right, if you start at v0, go around to vi, you come back to the same vertex, vi equals vj, and then you carry on to the end. Well, I can just break this closed walk up into two pieces, two smaller closed walks. I can go from v0 to vi, and then because vi is vj, I just pick up at vj and go back to v sub n, which is v0. That's one closed walk. And you have a closed walk from vi to vj. And one of those two closed walks is going to be odd because the sum of their lengths is odd. And they're both going to be shorter than the original. So I found a shorter closed walk of odd length, and that's a contradiction. And I'm not writing all of this out. You will find this in the notes. I'm hoping to do enough to sort of to convey this argument that you'll understand the notes when you're taking a careful look at them. Again, I think the key points here are like we're going to the contrapositive because it gives us a thing that we can take advantage of. I can't stress enough that when you are trying to prove things in graph theory, you want to turn your statements around. You want to think about contradiction. You want to think about contrapositive. And anytime you've got a form of a statement that allows you to take advantage of some graph structure, you can draw something or have some little thing in the graph, draw a picture of it, try and take advantage of that. Here, when we say contrapositive, I'm suddenly trying to prove that a closed walk of odd length will imply the presence of a cycle of odd length. If that closed walk didn't have repeated vertices, you're done already. Then that's giving you a cycle of odd length. If it does have repeated vertices, we have this trick of kind of breaking it up into two, and that allows us to find basically it allows us to find a shorter cycle of odd length. And you can express that proof algorithmically, or you could do what I've done. If you, at the start of the day, just choose a shortest walk of odd length, we will just verify that that is, in fact, going to have no repeated vertices other than the first equals the last, and so it will give you a cycle of odd length, and that's what I've done here. If you have a repeated vertex, then we break it up and we win. Okay, so that gets us property 2 implying property 3. Let me jump ahead to the next page. So let's remember what we're trying to prove here. So we have G is bipartite. This is implied that G has no cycle of odd length. We verified that this implies that G has no closed walk of odd length. Now we're going to go from the assumption that G has no closed walk of odd length, that's 3, to prove that it's bipartite. So what we still have to do is prove that no closed walk of odd length means that G is bipartite. So what remains to do is 3 implies 1. Excuse me. Okay, now for this part of the proof, it is going to be convenient for reasons that you'll see to work with a connected graph. In fact, we can do this without loss. So again, I'm trying to prove that if you have a graph with no closed walk of odd length, then it's bipartite. Well, what if you only knew this was true for connected graphs and I handed you a graph that was disconnected? It's got a component here and a component here. Well, this component does not have a closed walk of odd length, therefore it's bipartite, and that means it has a bipartition. Similarly, this component is going to have a bipartition, and you can just put those two bipartitions together and you get a bipartition of the big graph. So in other words, the validity of the thing that I'm trying to prove here, the validity of this for a connected graph or for a connected component, if that's true for every connected component, then it's true for the big graph. So it suffices to consider only connected graphs. Again, this statement, if you prove it for connected graphs, you can immediately deduce it for general graphs, because you just take your general graph and you do what we know how to do now. You say, well, okay, my general graph, it's just made up of these connected components. If this statement holds in each one of them, then I can just put this together and it's true for the whole graph. So I'm going to I'm going to say that very compactly here. I'm just going to say we may assume without loss of generality maybe I'll just, sorry, I shouldn't say that. Maybe I'll just say we may assume that G is connected. And again, I mean, I really am saying something that is, at least the first time I'm saying it here, really is a thing that you should think through very carefully. Again, I'm saying we can assume that G is connected. Why? Well, I'm going to give you a proof that works under the assumption that the graph is connected. If you have that proof, you can then take this and apply it to each connected component. So if I were to give you a graph that was not connected, we know that that then has all of these little connected components. You can apply this argument in each one of them, and that will give you what you want in the whole graph. So this is a very common feature, right? If you have a graph that's disconnected, I'd say it has two connected components here and here. Lots of times there's nothing happening in between the two of them, so it's pretty natural to imagine that you might have you can deduce the properties of the big graph from properties of the first component and the second, and that's that. So it's a common thing that we see, and I'm going to summarize it here very briefly. So again, I'm trying to prove this property. If it holds for every connected graph, then it holds for every graph just by applying it to the connected components. Okay, so now I'm safe in assuming that the graph is connected. And what we're going to do is an argument that something we saw a little bit before, and we will see this one again. What we're really going to do is we're going to kind of ground ourselves by choosing a base point. We're going to consider walks from that base point to other vertices. Okay, so this is the base point argument. So sensible to say that. So I'm going to choose a base point. I'll just put this in quotes. I'm putting this in quotes because this is a thing you see in a lot of other places in mathematics and topology or algebra somewhere, where you kind of need to ground yourself by putting something down, and lots of times we call that a base point. I'm not, this isn't something I'm defining formally, but this type of argument we'll see a couple times in class, and it's a good one to kind of keep track of. So we're going to choose a base point, vertex u, and now what I'm going to do is I'm going to try to use this vertex u to kind of classify the other vertices. Now, suppose I have some other vertex v out here. Well, you can walk from u to v, because I have a connected graph, you could walk along this walk w, or maybe you could walk along this walk w prime. So you're going to have, in general, lots and lots of different ways of getting from the vertex u to the vertex v. Now, if I take a walk from u to v, and then another walk from u to v, but go backward along that one. So I walk, again, I don't know why I'm gesturing in the sky here. Here's my vertex u, here's my vertex v. I'm going to show you two walks. I'm drawing them separately. But of course, they're allowed to run over the same vertices or edges. They're just walks, right? So here's my base point u. There's some other vertex v. Now, I can get from u to v by w. I can get from u to v by w prime. But I can use w and w prime. Oh, I should put an arrow in here. I can use w and w prime to form a closed walk, right? I could walk from u back to itself by walking out along w, and then reversing w prime, right? Walking out along w and then reversing my path from w prime back. If you do that, you get a closed walk from u to itself. And I know something about closed walks, right? We know that every closed walk has even length, right? That's the property we have. So we're assuming that our graph G has the property that there's no closed walk of odd length. So in other words, every closed walk has even length. Now, if you make this closed walk by going out along W and then back along W prime, if this walk has even length, that means that W and W prime, their lengths have to have the same parity. They're either both even or they're both odd, right? Because you're taking you've got the length of W plus the length of W prime is going to be an even number. So that means they're either both even or both odd. And that's the key to this. So the key observation here is that for every vertex V, when you look at all of the walks in the graph from U to V, they're either all odd in length or all even in length. So they all have the same parity. Oh, maybe I should say, sorry, let me quantify this property. So the observation is that for every vertex V, the lengths of all possible walks from U to V always have the same parity. So there are either all walks from U to V have odd length or all walks from U to V have even length. Or all walks U to V have odd length. Right, so there we are. So again, here's U and here's V, so we've we can get from U to V by W, we can get from U to V by W prime. Well, I can get from U to itself by going forward along W and backward along W prime. By assumption, all closed walks have to have even length, so that closed walk has even length, and that means that W and W prime, their lengths, they're either both even or they're both odd. They both have, their lengths have the same parity. And so what's happened here is we can now classify all of our vertices. So we fix this base point U. For every other vertex in the graph, it's either kind of the even type or the odd type. Either when I look at walks from U to that vertex, they all have odd length or they all have even length. And that gives us a natural split of our vertices into two sets. And that is indeed the essence of the proof. So now I'm going to, or in fact, let's use the word define. Let's define A. This is going to be the set of all vertices so that there's a walk of even length from A to B. There's a walk of even length from U to V. So that's my set A. And here's my set B. So B is going to be the set of all vertices with the feature that there exists a walk from U to V of odd length. Now, our observation here is telling us that A intersect B is empty, right? You do not have a vertex with the feature that there exists both a walk of even length from U to V and a walk of odd length from U to V. So our observation is telling us that A intersect B is empty. A union B is going to be everything, right? My graph is connected. Right? My graph is connected, so there must be some walk from U to every other vertex in the graph. And that means that every vertex has to be in one of A or B, in at least one of A or B, and we've just verified that you can't be in both. So what we've got here is, thanks to the connectivity, we know that A union B is everything. I know that A intersect B is empty. That's by our observation. Now, what I claim is that in fact A comma B is a bipartition. And I'm just going to draw a picture here to indicate why that's true. So why is it the case that you could not have an edge joining two vertices in A? Right, so I should say at the start, maybe, if we can prove this claim, then we're done, right? We've found a split of our vertices into a left set and a right set. I'm now claiming that every edge has to have both ends, sorry, it has to have one end in the left and one in the right. So to prove that, and again, you see I'm taking advantage of contradiction. So how am I going to prove that? Well, suppose it's violated. If it's violated, then I'm giving you an edge, right? And here's our edge. Suppose there's a violation. Suppose there's some edge of our graph that has both ends in the set A. Well, if that happens, what's going on? That means I've got a vertex here. Sorry, my pen is not the best here. So I've got two vertices, say V and V prime, and they're both in A, and there's an edge between them. Well, what does it mean to be in the set A? That means that there's a walk from U to that vertex V of even length. That's what it means to be in the set A. What if you take that walk from U to V and you just append this little edge and walk to V prime? Well, that's giving you a walk from U to V prime that's one step longer than our walk from U to V. Well, if the walk from U to V was even, this one's going to be odd. And that contradicts the fact that V prime is also in A, right? So if I give you, anytime I gave you an edge in the graph, well, if you have a walk from U to one end of this edge, I can follow this, I can traverse this edge, and I get a walk from U to the other end of this edge. And, excuse me, and those two walks are differing in length by 1. So if this vertex was in the set A, and that walk was even length, then this other one's going to be odd, and that one has to be in B. And conversely, if this first vertex was in B, then then that walk from U to this vertex was odd in length, and then when I traverse this, I'm going to have an even length walk, and that puts that vertex in the set A. So what this means is you can't have an edge of the graph with both ends in A, and you can't have an edge of the graph with both ends in B, or in other words, every edge of the graph has to have one end in A and one end in B, and then we're done. And now we've found a bipartition of our graph. And I'm going to wrap up the set of notes there.